Okay, hello everybody. This is Dr. Hussein in Calculus and Linear Algebra. This is week number 6. We're still in Module 2, which is related to solve system of equations and eigenvalues of matrices. Today we will use eigenvectors and values and vectors to solve set of differential equations. Okay. So let me back to eigenvalue and eigenvector to practice more. We discussed this. We mentioned that we will go through the characteristic equations to find eigenvalue, and for each eigenvalue we'll find eigenvector. Example here, you are given this matrix. This is the matrix A, okay, and in this matrix what we have, as you can see, so what we have is the characteristic equation. You remember characteristic equation is determinant A minus lambda I identity equals 0. So we will substitute. This is A, as you can see here. This is lambda minus, this is identity. Then we solve. Okay, lambda will be here, and 3 minus lambda will give me 3 minus lambda minus 1 minus 0 minus, and so on. We got this formula. Now we multiply these two items with these two items, subtract them, as you can see here. Take care of these signs. Minus minus minus, it will give minus. And then we simplify, we go to quadratic equation. We solve it either by factorization, quadratic formula. As example, I here solve it by quadratic formula to find the two items, the two eigenvalues, lambda 2, lambda 4. Okay. Now another example to find the eigenvalues is you are given this matrix A. Okay. Again, it's the same procedure. Numbers change, but the procedure is the same. As you can see here, A, lambda, and I. Subtract, multiply this item. We got this formula. You solve it to find eigenvalues 2 and 3. For each one of them there is eigenvector. As example, for this lambda 1 we have this eigenvector. Try to solve to find eigenvector, similar to the examples solved in the week number 5. The same thing for 3, we have another eigenvector. Please solve them, try to practice on them. Okay, another example here, you are given this matrix A. Okay, you see I changed numbers only. The determinant here, as you can see, this is A, lambda, I. We multiply these items, as you can see here, and then we simplify. We have this formula to get a quadratic formula. We solve it, we find lambda equal minus 1. Okay, it's repetitive, okay, twice, because here you have square. So for this lambda minus 1, we have, as you remember, Ax equal lambda x, or let me say, sometimes they call it u. It doesn't matter, it's vector at the end. Okay, so we have to substitute. This is the A minus lambda I, and this is x equal minus x. Okay, now which is 0, supposed to be 0 here to satisfy the condition. Now we substitute for lambda here, this one by minus 1 and this one by minus 1. We got this part. Now if I multiply this row by this column equals 0, I got equation which tell me that this is correct equation in only when x1 and x2 are equal. So I can't write the x1 and x2. It could be any value, t as example, in this way. So we can't take t as a common. What is left? 1 1. So this is the eigenvector. Now for diagonalization, the idea is when we have a matrix A, there is invertible matrix, which can be invertible to become inverse. Okay, so its determinant is not equal to 0. Okay, in a way that if we multiply the matrix, the new matrix P to inverse matrix by A times B in this arrangement, then we have the diagonal which contain the eigenvalues. How I will show you how we work on this. Have a look at this matrix A. I will come to find first the eigenvalue and then the eigenvector. I go through the characteristic equation minus lambda I, similar to the previous example. I got equation, characteristic equation, then I solve it. I found lambda 2 and lambda 1. Now for lambda 2, I go through the same procedure to find eigenvectors. I found two eigenvectors, 1 and 2, and here one eigenvector. So I have 3 columns. These 3 columns, I will take them and construct matrix. This is the matrix. This matrix, I call it P. Why? This is diagonal matrix. Okay, diagonalized matrix. Why? Because if I go at P inverse, We know how to do P inverse. We have different methods. And I multiply P inverse times A times the P. A is my original matrix. As you can see here, this is P inverse. I got it. There is work to be done here. This is A and this is P. I got this matrix. What this matrix contain? See the diagonal. It is a diagonal matrix where these numbers represent the eigenvalues 2, 2, 1 of the matrix. Let's see another example. A matrix that is not diagonalizable. Okay, find the matrix P that is not diagonalizable. He told me that the matrix here is not diagonalizable. P inverse A P will not give D, which is the lambda 1, lambda 2, lambda 3, as I mentioned, 0, 0, 0, 0, 0 in this way. It will not give. Let's see. Let's assume we will work on this. I come to the characteristic equations. I approach here. I did the determinant. I got characteristic equation this way. I solve it. I go to lambda 1 and lambda equal 2. When I come to find the eigenvector for this lambda, this eigenvalue, I got one vector. And for this one, I got one vector, which is for 2. When I concentrate them, we can see there is one column, two column. It's not 3 by 3. So for that, it is not diagonalizable. It's supposed to be 3 by 3. Now, theorem. Let's describe this theorem related to diagonalizability. If M by N matrix A has N distant next eigenvalues, then A is diagonalizable because we have 3 eigenvectors. See this matrix? When we solve it to find eigenvalues and eigenvectors, we got these values.